Assalamualaikum warahmatullahi wabarakatuh. Good afternoon. Today we continue chapter 4 about DC biasing BJT. Okay, after we learn about the basic BGT, today we will learn how to turn on the BGT in the circuit. As we know that when the purpose or um, the function of BJT is amplifications. So it means that we amplify the AC signal. So if we have the AC signal is like the from the electricity from the in our house is basically the AC. So we have the AC, the input AC, and then we have the amplifier here, and then we got the AC here. So this is the input AC, AC voltage, and then the output is AC voltage. And we using the amplifier here to amplify. It means that we want to increase the magnitude of the AC input to the AC output. So how to amplify this one? We can use the bipolar junction transistor. So the bipolar junction transistor can amplify the signal, and in order to amplify the signal, we have to turn on the bipolar junction transistor first, or we have to put the bipolar junction transistor in the specific operations. As we know that we have three modes of the bipolar junction transistor. The first one is saturations, and then the forward or active region, and then the cutoff. In amplifier mode, if we want to use the bipolar junction transistor in amplifier mode, we have to put the BGT in active region mode. Okay, so how to decide that BGT in the in active region mode? So we learn here. We learn how to turn on the BGT in the active region mode, or we turn on the BGT in saturation mode. And saturation mode and cut off mode is very useful for BGT in switching application. So in another application of the BGT, okay, commonly BGT is we can use as like amplifier, and then another is we can use as a switch. Okay, switch. And for amplifier, we use the active region mode. And for switching, we use the saturation region for on, and then we use the cutoff to turn off the BGT. Okay, here. So how to turn on the BGT in active region, saturation, or cutoff, we will learn here in the DC biasing. So the first one, you have to remember that the VBE is 0.7 volt for the silicon, and then the IE emitter currents is beta plus 2 IB, or similar to IC, and IC is beta IB. Okay. Okay, so this is we have a three region here. This is the saturation region, the shaded area here. So this is the saturation region, and then this is the cutoff region, and then the white region is the active region. Okay. Okay, so in linear region is similar to active region. Yeah, this is the active region. So the base emitter junction is forward bias, and base collector is reverse bias. In cutoff, two junction in reverse bias in saturation region, two junction in forward region. Okay. So how to design the three of this region? The first one, we can use the fixed bias circuit like this one. So fixed bias is basically you can learn from this graphic. This is the BGT, NPN BJT, we connect to base using the base resistor and the collector using the collector resistor, and we connect to VCC here. And we have the AC input signal here and AC output signal here. Okay, so in DC biasing, we only learn how to turn on the BJT in this area. So we didn't learn, or maybe after midterm test, we will learn the total amplification of the BJT. It means that we will use the AC input signal and AC output signal. But for DC biasing, we only concentrate in this area. It means that we have the coupling capacitor C1 and coupling capacitor C2 here. So the current didn't flow to here. So if we have the current from the AC, we have the current here. So the coupling capacitor C1 and C2 is the coupling capacitor. Coupling capacitor is to prevent the current, the DC current in the fixed bias to go to the input signal or the output signal. So we use the capacitor as we know that the capacitor has the very high impedance in the DC. So if you notice that XC is 1 per omega C, this one, yeah, in physics you learn about this one. So if we use the DC, it means that the omega here is 2VF and the F is 0 for the DC. So the XC, the capacitive impedance, is very high for the DC. So here is very high resistor here, or very high impedance here. So the current, the DC current cannot through pass to the AC signal and AC output signal because of the impedance in C1 and also the impedance in C2 is very large here. Okay, so how to analyze this characteristic? The first one, we use this one. We use the Kirchhoff. So this is from the base resistor. We can see here plus VCC. So base resistor here, the loop here plus VCC minus IB RB plus minus VBE is equal to 0. So IB is VCC minus VBE per RB. Okay, and we know that IC is beta IB. So here in collector emitter loop, VCE here, this is the VCE, plus ICRC minus VCC is equal to 0. So VCE is equal to VCC minus ICRC. And then VCE is VC minus VE here. So because of VE is equal to 0, so VCE is equal to VCE, and VBE is equal to VB minus VE. And VE is equal to 0, so VBE is equal to VB. Okay, so for example, let's determine the following for the fixed bias. So what is the IBQ and ICQ here? So IBQ, we use the Kirchhoff here. So we can analyze this loop, or using the previous mathematics, we see that IBQ is VCC minus VBE per RB. So VCC is 12 volt. VBE is 0.7 here, as I remember I explained before, and then RB is 240 kilo ohm. So we can get that IBQ is 47.08 microampere, and ICQ is beta IBQ. So we can get that beta is 50, this one. So we can get that ICQ is 2.35 milliampere. And then B is VCEQ. VCE is VCC minus ICRC. IC is 2.35. So we can get the 12 minus 2.35. RC is 2.2 kilo ohm. So we can get that VCEQ is 6.83 volt. And VB or VBE is 0.7. And VC and VCE is 6.83 here. Okay, VCE, because VE is 0, connect to ground. Or VBC is VB minus VC, 0.7 minus 6.83, so we can get minus 6.13 volts. Okay, so negative sign is mean that the junction is reverse bias. So because of the junction is reverse bias from the base to collector, it means that this is the linear amplification. Okay. So this is the transistor saturation. If the transistor saturation in this one, I mean that in preface, this is the saturation. So it's near to 0 volt. So RCE is equal to VCE minus IC. This is the VCE. So near to 0. So VCE, we assume that 0. So we can get that RCE is equal to 0. So IC sat is VCC per RC. Okay. Okay, this is the load line. So if we want to draw the BJT characteristic, we can use the load line like this one. Okay. So the first one, in order to draw the load line, we have to draw, or we make in x-axis and y-axis here. So first one, we have to put the cross section in y-axis in here. So VCE is equal to VCC minus ICRC. The first one, when the IC is equal to 0, so here, so we can get the here in x-axis. So IC is VCC per RC when the VCE is equal to 0. Okay, and then when IC is equal to 0, so VCE is equal to VCC. So we have a 2 point here. The first one here in y-axis and another in x-axis here. So we draw from this point to this point. So we can determine the key point here. This is the IBQ. Okay. So the key point we can move the key point if we use difference current here. So if we have the IB1 here, IB2 and IB3, the key point can move from the 1 here to the 3 here. Okay. And also we can change the VCC. The first one here, we change the IB, or base current. If we change the VCC, the load line will change from here to here. So the key point will change. Or we can also change the collector resistor here. Yeah, R3, this is the collector resistor. So if we change the collector resistor, the load line will change like this one. Okay. And this is if we change the VCC here, VCC1, VCC2, and VCC3, the key point also changes. Okay, so this one, the first part of the DC biasing. After this one, we will discuss about the emitter biasing configuration. Thank you for your attention. Good afternoon. Assalamualaikum warahmatullahi wabarakatuh.